My name is Michio Kaku, and today we're going to explore a question that has puzzled scientists for a quarter of a century. Why is the universe expanding faster and faster? For decades, the answer seemed simple on paper: dark energy, a mysterious form of energy that pushes galaxies apart. It fit into Einstein's equations, made the numbers work, and helped cosmologists stitch together a model of the universe that explained almost everything we observed. But there has always been one problem. We have never detected dark energy, not once. Not in any laboratory, not in any particle accelerator, not in any cosmic survey. It has remained a ghost in our equations, a placeholder for something we've never actually seen. And now, a new study suggests we may not need it at all. Tonight we're going to break down a bold idea coming from an international team of researchers, an idea that proposes the universe's acceleration might not be caused by a mysterious energy permeating space, but instead by the geometry of space-time itself. If that sounds radical, that's because it is. For the first time in decades, we may be looking at a framework where cosmic acceleration emerges naturally, without adding any new ingredients to the universe. And to understand how revolutionary that is, we need to go back to where all this began. In the late 1990s, astronomers studying distant type Ia supernovae noticed something strange. These exploding stars, normally used as standard candles to measure cosmic distances, were dimmer than expected. That meant they were farther away than we predicted. And if they were farther away, it could only mean one thing. The expansion of the universe was accelerating. This was shocking. The prevailing expectation was that gravity should slow everything down over time. Instead, space itself was pushing outward faster and faster. Cosmologists scrambled to explain this cosmic surprise, and dark energy became the leading candidate. Roughly 68% of the universe, we were told, was made of this invisible, undetectable energy. It worked mathematically, but it raised as many questions as it answered. Now imagine, after 25 years, someone walks in and says, what if the acceleration isn't caused by some ghostly energy after all? What if space-time itself behaves differently on large scales than we assumed? That's precisely the argument behind the new study published in the Journal of Cosmology and Astroparticle Physics. It comes from teams at Centrum Favant, Technology Microgravitation, and Transian University of Brash. Instead of adding a new component to the universe, they modified the underlying geometry of Einstein's equations using something called Finsler geometry. So what is Finsler geometry? Most people are familiar with Euclidean geometry, the geometry of flat surfaces, and some have heard of Riemannian geometry, which is what Einstein used to build general relativity. These frameworks assume that space-time is smooth, continuous, and behaves uniformly in all directions. But Finsler geometry relaxes one of these assumptions. Instead of treating space-time the same in every direction, it allows the geometry to depend slightly on direction or on the motion of objects within it. The change is subtle, almost imperceptible at small scales. But on cosmic scales, when we're talking billions of light years, those tiny differences can accumulate into something profound. Using this framework, the researchers extended the Friedmann equations, the mathematical engine that describes the expansion of the universe. What they found was astonishing. Even in a vacuum, even with no dark energy term at all, the equations naturally produced accelerated expansion. It simply emerged from the structure of space-time, as if the universe itself had a built-in tendency to speed up over time. This result doesn't rewrite cosmology overnight. It doesn't overthrow decades of data, but it does something far more elegant. It removes an assumption. Instead of postulating a mysterious energy to explain the acceleration, it suggests that the acceleration may be a fundamental geometric effect. The universe isn't being pushed by something unknown. It may simply be behaving according to deeper rules we haven't considered before. To understand why this approach is so fascinating, let me put it this way. When Einstein introduced general relativity, he changed the game by showing that gravity wasn't a force. It was geometry. Matter tells space-time how to curve, and spacetime tells matter how to move. Now imagine that after a century of using Einstein's geometry, we discover that the geometry itself may need a small extension to fully describe the universe. Not a new energy, not a new particle, not a new force, just a deeper understanding of the geometry that underlies everything. For years, cosmologists have used the lambda cold dark matter model, lambda cold dark matter, to describe the universe. Lambda represents dark energy, CDM refers to cold dark matter, and together they form the backbone of modern cosmology. The model fits observations remarkably well. It explains the cosmic microwave background, galaxy clustering, gravitational lensing, and the large-scale structure of the universe. But lambda, dark energy, has always been the odd one out. An elegant model built on a questionable foundation, a patch added to the equations to make everything line up. The new Finsler-based approach suggests that lambda may not be a substance at all. It could be a mathematical parameter pointing toward a deeper structure of spacetime, much like early astronomers added epicycles to planetary motions before Newton revealed the true mechanics. This doesn't make dark energy wrong. It simply means we may have been describing a phenomenon rather than identifying a cause. One of the most important aspects of this new study is that it does not contradict the observations that built the standard model. The researchers specifically ensured that at lower energy levels, to which most of our observations belong, their extended geometry reduces back to standard cosmology. This means galaxies, clusters, and local structures still behave exactly as we expect. The innovation appears only when we zoom out to cosmic scales. Think of it like this. If you look at a flat Earth map, everything seems normal. But when you zoom out far enough, the curvature of Earth becomes impossible to ignore. This study argues that something similar may be happening with space-time. On local scales, geometry behaves as Einstein predicted. But across the entire universe, the geometry might bend in ways that produce accelerated expansion automatically. Now, before we jump to conclusions, it's important to remember that this is still just the beginning. New ideas in cosmology must survive a gauntlet of tests before they can be accepted. But the beauty of this study lies in its simplicity. Instead of adding something new to the cosmos, it removes something and asks whether the universe might be simpler than we thought. Could cosmic acceleration be written into the very fabric of space-time? Could dark energy be an illusion created by our assumptions? In the next part, we'll explore why this idea matters scientifically, how it compares to other modified gravity theories, and what it means for the future of cosmology. When we left off, we introduced a bold idea that the accelerating expansion of the universe may not require dark energy at all. Instead, it might emerge naturally from the geometry of space-time itself. If true, this would be one of the most profound shifts in cosmology since Einstein rewrote gravity in terms of curvature. Now let's explore why this idea is scientifically exciting, how it fits into the broader landscape of theoretical physics, and what it could mean for the future of our understanding of the cosmos. For decades, dark energy has been the backbone of the lambda CDM model, the standard framework of cosmology. It has helped us explain nearly every major observation, from the faint afterglow of the Big Bang to the distribution of galaxies across cosmic webs. But despite its success, dark energy has always been a placeholder, an unknown force added to equations to match the data. Imagine building a beautiful machine, watching it work flawlessly, but knowing that one crucial component is something you made up because otherwise the gears wouldn't turn. That's dark energy, useful, powerful, but mysterious. That's why any alternative explanation that preserves the success of the standard model while removing this mysterious ingredient is worth examining closely. One of the most compelling aspects of the Finsler geometry approach is its elegance. Instead of inventing new forms of energy, it modifies the structure of space-time in a subtle and mathematically consistent way. In theoretical physics, we often say that the best ideas are the ones that reduce complexity rather than add to it. Einstein himself believed in simplicity. He once said that everything should be made as simple as possible, but not simpler. This new approach embodies that spirit. It doesn't claim that the universe is filled with an exotic, invisible energy. It suggests we may have overlooked a deeper geometric property built into space-time from the beginning. To understand why this matters, consider the nature of general relativity. Einstein turned gravity into geometry. Matter tells space-time how to curve, and space-time tells matter how to move. This beautiful relationship is encoded in the Einstein field equations. But these equations rely on a specific type of geometry, Riemannian geometry, where distances and curvature behave uniformly in all directions. It has served us extremely well. But as our observational tools grow sharper and we push into the furthest depths of the universe, we may need a more flexible mathematical framework. That's where Finsler geometry enters the picture. In Finsler geometry, space-time can depend not only on position, but also on direction or motion. This doesn't break Einstein's theory. It generalizes it. And just like general relativity reduces to Newtonian gravity at small speeds and weak fields, Finsler geometry reduces to standard relativity at familiar scales. But at cosmic distances, billions of light years, these subtle directional dependencies can accumulate, creating effects that mimic dark energy without requiring it to exist. In other words, what we thought was a mysterious force pushing the universe apart might simply be a geometric feature emerging as we look farther and farther into space. This is not the first time theorists have tried to tweak gravity to explain cosmic acceleration. Many modified gravity theories, such as FR gravity, brane-world models, and emergent spacetime approaches, have attempted to replicate the effects of dark energy through alternative mechanisms. Some of these proposals add extra dimensions, others modify Einstein's equations directly. But the Finsler-based approach stands out because it doesn't add new fields, new dimensions, or new particles. Instead, it deepens the geometry itself. It's like discovering that the blueprint of the house was always more intricate than we realized. Now, let's talk about why this idea is scientifically compelling beyond its elegance. One reason is that it does not create new conflicts with existing observations. The authors of the study ensured that their model remains consistent with the wealth of cosmological data collected over the past several decades. For instance, the cosmic microwave background, often called the baby picture of the universe, contains tiny fluctuations that reveal the geometry of the cosmos at early times. Any new model must reproduce these patterns accurately. The Finsler framework, at least in its current form, does not contradict these measurements. Another reason this idea is intriguing is that it reframes the meaning of cosmic acceleration. Rather than adding something to the universe, it asks whether the universe itself may have properties we haven't fully appreciated. Think of it like discovering that the floor beneath you is not perfectly flat but slightly curved. You don't need to invoke a mysterious force to explain why a ball rolls in a certain direction. It's simply responding to the shape of the floor. Likewise, cosmic acceleration might be the natural response of space-time to its deeper geometric structure. This perspective also opens an exciting door to quantum gravity, the holy grail of modern theoretical physics. Many physicists believe that at the smallest scales, space-time may not be smooth at all. It might be grainy, foamy, or governed by principles beyond classical geometry. If Finsler geometry turns out to be a meaningful extension on cosmic scales, it could signal that geometry itself is richer than we thought, linking the behavior of the universe at the largest scales with the structure of space-time at the smallest. In other words, this could be a bridge between cosmology and quantum gravity, something we've been searching for since the days of Einstein. But ideas in physics are not judged by elegance alone. They must be tested, challenged, and stressed until they either break or survive. The next step for this theory is to confront observational data head-on. Cosmic acceleration was discovered through supernova measurements, and these remain a key test. Any new model must reproduce the brightness-distance relationship of type Ia supernovae with high precision. It must also match the baryon acoustic oscillation data, which act as cosmic rulers probing the universe's expansion history. It must align with gravitational lensing surveys that map how matter bends light on large scales. And perhaps most importantly, it must explain how galaxies, clusters, and the cosmic web formed over billions of years. This last point is crucial. Cosmic acceleration doesn't just affect the expansion of the universe. It influences how structures grow and evolve. If the geometry of space-time itself drives acceleration, then the way matter clumps together might differ from predictions of the standard model. This could leave subtle fingerprints in our observations, differences in lensing patterns, deviations in structure formation, or shifts in the growth rate of cosmic density fluctuations. These signatures will either validate or rule out the new geometric framework. For now, dark energy remains the dominant explanation because it fits consistently with everything we've observed. But science advances by questioning assumptions, exploring alternatives, and testing bold ideas. This geometric approach doesn't claim to have all the answers, but it does offer a new lens through which to view one of the biggest mysteries in cosmology. And sometimes that's how revolutions begin, not with the discovery of something new, but with the realization that what we already have may hold deeper secrets than we imagined. As we move toward the conclusion of this exploration, we arrive at the most important question of all. Can this new geometric explanation truly replace dark energy? In science, bold ideas often spark excitement, but they must withstand rigorous testing before they can rewrite textbooks. And that's where this journey now leads us, to the challenges ahead, the data we must confront, and the implications for our understanding of the universe. Let's begin with the tests that lie directly ahead. The first and most crucial is the one that started this entire mystery back in the 1990s, Type Ia supernovae. These brilliant stellar explosions acted as cosmic mile markers, revealing for the first time that distant galaxies were accelerating away from us. Any new model must reproduce those results with astonishing accuracy. If the Finsler-based framework can match the supernova data without invoking dark energy, it will pass one of its greatest hurdles. But supernovae are only the beginning. Next, we have the cosmic microwave background, the faint radiation left over from the Big Bang. Tiny temperature variations in the CMB encode the geometry of the early universe with exquisite detail. The lambda CDM model fits this data almost perfectly. That's one of the reasons dark energy became so widely accepted. If the new geometric model can match these same patterns, same peaks, same amplitudes, same angular scales, it will demonstrate that its foundation is just as solid as the standard models. But if it deviates too far, cosmologists will know immediately that the geometry needs refinement. Then there are baryon acoustic oscillations, the ripples from ancient sound waves frozen into the distribution of galaxies. Think of them as cosmic rulers that let us map the expansion history of the universe. These measurements have been a powerful check on the lambda cold dark matter model. Any alternative must predict the same cosmic scale with precision. Even a small discrepancy can reveal whether the geometry-driven acceleration holds up under scrutiny. But perhaps the most challenging test involves the growth of structure itself. Cosmic acceleration doesn't just change distances. It affects how galaxies and clusters form over billions of years. If the geometry of spacetime drives acceleration, then matter might clump together differently than in the standard model. Subtle differences in gravitational lensing, in the distribution of galaxy clusters, or in the rate of structure growth might reveal whether this geometric explanation aligns with reality, or whether the universe prefers the older, familiar interpretation. This is the beauty and the burden of scientific progress. Every new idea, no matter how brilliant, must pass through the same gauntlet. It must match observations, withstand critique, and survive repeated challenges. And only then can it claim any authority over how we think the cosmos works. The Finsler-based approach is elegant, yes. It simplifies the story of cosmic acceleration. It might even be right. But the universe is the final judge, and the data will decide. Still, Let's consider what it would mean if this idea holds up. Imagine a universe where acceleration is not driven by an unseen force, but is instead woven into the fabric of space-time. A universe where geometry itself, subtle, directional, dynamic, guides the expansion of everything. This would not just adjust our understanding of cosmology, it would reshape the relationship between gravity, geometry, and the very laws that define reality. It could provide a bridge toward quantum gravity, linking the vastness of the cosmos with the smallest scales of existence. It might tell us that space-time is more flexible, more textured, and more complex than we ever imagined. And it would offer something else, simplicity. Instead of filling the universe with an unknown energy that we've never detected, we would be peeling away a layer of assumption and revealing a deeper truth. That's one of the greatest triumphs of physics, finding out that the universe is not only stranger than we imagine, but also more elegant. But until then, we must remain cautious. Dark energy remains the dominant explanation because it works. It fits the CMB, it fits supernovae, it fits gravitational lensing, it fits the expansion rate with remarkable consistency. And while it remains mysterious, it has earned its place by matching decades of observational evidence. Replacing it requires something truly extraordinary. The geometric approach is promising, but its journey has just begun. In the coming years, new telescopes and observatories like the Vera Rubin Observatory, Euclid, and the James Webb Space Telescope will gather data that could challenge or confirm this emerging picture. If accelerated expansion turns out to be a geometric effect, these instruments will see the signs. And if not, they'll strengthen the case for dark energy even further. That's the beauty of the scientific process. No idea is sacred. No theory is untouchable. Only evidence decides. So as we close, remember this. Science thrives on curiosity, on challenges, on questions that force us to rethink what we believe. This new study doesn't demand that we abandon dark energy, but it invites us to look deeper, to ask whether the universe might have secrets hidden in the very geometry of space-time, and whether cosmic acceleration, the phenomenon that has baffled us for decades, is not a force pushing outward, but a whisper from the universe's underlying structure. I'm Michio Kaku, and if this research holds up, we may be standing at the edge of a new revolution in cosmology, one where geometry, not mystery, drives the expansion of the universe. The next step is clear. Test the idea, examine the data, and let the cosmos reveal its truth.